When we study waves, one of the important phenomena to pay attention to is two-source interference. And I'm going to do an example here using water waves, just because that's not the most common thing we see in class, and so it seems like something different to talk about. But the phenomena here apply to all types of waves. In fact, this is very similar to a laser double slit experiment you might do in a lab, for example. So how does this work? Imagine that I have a set of waves, water waves, coming toward the shore, and at some particular point, there are some rocky outcroppings that block the water from reaching the shore. But there are a couple of holes in the rocks. And those holes are a distance d of 24 meters apart, center to center distance, 24 meters apart. And I'm going to assume for this particular example that the wavelength of the waves coming in is about 6 meters. So noticeably smaller than the separation between these two holes in the rocks. On the other side, in what would normally be calm waters, we have open space, open water going along up until some cliffs on this side. And when the waves reach the cliffs, they splash against the cliffs. And what we're going to find in this story is that there's some locations along the cliffs where that splashing will be most prevalent, where you'll see big splashes, high amplitude of the waves. Those will be points of constructive interference that hopefully you've learned about in general in some other way. This is just applying some equations. So on the other hand, there will be places where there's very little sloshing against the cliffs, and those will be points of destructive interference. And for simplicity, I'm assuming the cliff is basically straight along here. I made it a cliff and not a beach, so I can assume I have a constant depth here, just in case that might mess with the wavelength in some way. So we're going to keep this as being a fixed wavelength coming along through this whole story until the waves splash up against the cliffs. The cliffs are 120 meters away from these rocky outcroppings out blocking the waves earlier. And by the way, I'll also point out that the openings in the rocks are small enough, they're smaller than this wavelength of 6 meters, and that will mean that the waves, when they come through the opening, will not just give a narrow beam of sloshing on the other side, but will spread out in all directions. That single slit diffraction where the waves spread out is its own topic. We're going to focus, just assuming it happens, we're going to focus on broad spreading from both these slits and where we get splashes along the cliffs. In particular, I want to know if I'm standing at the top of the cliff above the central splashing point, right in a straight line away from there, how far along the cliff do I need to walk to get to the next point where I'll see significant splashing, the next point of constructive interference? All right, so that's my goal in this problem and what I want to look at here. To answer this, we're going to need two things. The first one, hopefully you've seen a derivation of this somewhere because I'm not going to try to derive it for you. The first thing is the equation for angles of constructive interference in a two-source problem. Whether it's two holes in a breakwater here, whether it's two slits for a laser, whether it's two loudspeakers in sync, whatever it is, the condition for constructive interference in a two-source problem is this. The distance between the sources times the sine of an angle for constructive interference is going to be equal to n times lambda, n times the wavelength, where n is any integer. N could be -1, 0, 1, 2, and so on. Any integer, positive, negative, or 0. In particular, n equals 0 will give me a 0 on this side, and that will correspond to theta equals 0, sine of theta equals 0. Theta, as shown here, is measured away from the straight line. So theta equals 0 is the straight line point there, and fundamentally the reason that theta equals 0 is always a point of constructive interference is that it is the same distance from both sources. Along that central line, by definition, is the same distance from both sources, so the two sources will be in phase, and they will have constructive interference. Both ripples will build together and make a splash there. So I want to know how far I need to walk to get up to the next point of constructive interference. Well, just like this point in the middle here was my n equals 0 point, this one must be n equals 1. Down here would be n equals -1, n equals -2, n equals plus 2 would be the one that's just starting at the top of the board there. That's how we do this. The n's count how many points of constructive interference we have. And so I want to solve for that angle. I'm going to go through this, going through step by step, and then we'll talk about some shortcuts we could take. But solving for that angle, what I find is that the sine of my theta constructive number 1 is equal to, well, it's n lambda over d. And so that's 1 times my lambda is 6 meters. My d is 24 meters, according to the picture. Lambda is the wavelength, d is the distance between these. And as it must, the meters cancel out. This turns out to be 6 over 24. That's just 0.25. No units. It is crucial that sine, cosine, tangent, all of those are unitless quantities. They should always give no units. So 0.25 is sine of theta. If I work that out, I plug it into my calculator, and I can find that my constructive interference point number 1 is going to be, well, it's the inverse sine, arc sine, of n lambda over d. And so that is the inverse sine of 0.25. When I work out that number, I did this in my calculator earlier, I won't force you to watch me type it in. I get that this is about 14.48 degrees. In degrees, that's a relatively small angle, not that small, but relatively small. Or, important point, I could also write this as about, where is this, 0.2527 radians. Remember, radians, 2 pi radians is a full circle, so 0.2527 radians is about a quarter of a radian, 1/6, whatever. Yeah, so anyway, you can calculate this out. Quarter of a radian, that's interesting. 0.2527 is actually really similar to 0.25. That's only about 1% different between the angle between sine of theta and theta when we have a relatively small angle. 14 degrees isn't that small, but it's kind of small, and we're only 1% different between those. It's actually an important point that that's true. We'll come back to it later. So I've got my angle. Now I want to say, well, what's my distance s here? How do I deal with that? And to find that distance, well, I have a right triangle in this picture. I've got my L, my distance from the sources going over to the cliffs that way. I've got my S along the cliffs. This is a right triangle. And so I can immediately say, based on that right triangle, that the tangent of my angle, my constructive interference angle number 1, has to be equal to opposite divided by adjacent, S over L. And so I can conclude then that S is equal to L times the tangent of theta. I've got that. That's going to be true. What is tangent of theta? Well, tangent of theta equals, if I plug that into my calculator, I find that my tangent of theta is 0.2582, I believe. 0.2582 is my tangent. Again, that's really close to the sine of theta. We'll talk about that in a bit. For small angles, those are always going to be similar numbers. So, okay, that's my tangent. And so that tells me then that my S is equal to 120 meters times that tangent of that angle. I'll just put the number in. 120 meters times 0.2582. And putting that together, when I multiply it, I guess that's approximately 31.0. Again, I put in 31.0 meters is what I get when I plug that into my calculator. I won't make you watch me type it in. So that's my answer. I have to walk 31 meters along the cliff to get from the first splashy point to the second splashy point, from one point of constructive interference to another. All right, so that's the basic answer here, and we could stop right here. But let me ask 2 more questions. The first question is, how many angles will have constructive interference in this problem? At how many different angles? Because clearly at theta equals 0, I have a big splashy point. And clearly at theta equals 14.5 degrees, I have big splashes on the cliff. How many angles will have that happen? Well, I guess we could make a list if we really wanted to. We could say that I had, for n equals 0, I had theta equals 0, sort of by definition, 0 right there. For n equals 1, I had theta equals 14.5 degrees, more or less, 14.48 degrees. I had that for n equals 2. What would happen if I put in n equals 2 here? Well, I'd have another angle, 2 times lambda over d, twice as much as this, 0.5, inverse sine of 0.5. That actually you might know, the inverse sine of 1/2 is theta equals 30 degrees. That is another one. N equals 3, I could do the same thing. I guess I should write this down. This is the inverse sine of 0. This is the inverse sine of 0.25, like we did above. This is the inverse sine of 0.5. So theta equals, well, what will this be? It's going to be the inverse sine of 0.75. And if I plug that into a calculator, I can do that. I get 48.6 degrees as my next angle along the way. I can keep going. N equals 4. Theta equals, well, it's got to be the inverse sine of 4 times 0.25 is 1. And that is 90 degrees. Okay, that's interesting. And then n equals 5 would be, well, it would be the inverse sine of 1.25. And that doesn't exist. That's not allowed. Because you can't sine, the sine function goes as high as 1 and as low as -1, plus 1, -1, plus 1, -1. Sine of theta never gets up to 1.25, so there's no such thing as the inverse sine of 1.25. Your calculator gives an error. It doesn't exist. So there is no theta for n equals 5. That tells me that I only have 0, 1, 2, 3, and 4, and -1, -2, -3, -4 for the other direction. So I guess that gives me a total of 9 angles that'll work. And the 90-degree angle is interesting. That is, 0 degrees is straight, 14, 30, 48, 90 means there will actually be some reinforcement, noticeable ripples going this way, right along the inside of the breakwater. So that's an interesting observation, that you'll have some substantial ripple going right along the inside. All right, that's one follow-up comment I wanted to make. The other follow-up comment I wanted to make, so I hope that tells you how this works, how you can look at how many ripples there are, how many angles of constructive interference there are going to be. And for each one of these, I can figure out how far I have to walk along the shore to get there. I could do the same thing. Take my inverse tangent, take my tangent of these angles and multiply by L. It'll be farther and farther. I guess for the 90-degree one, I'm never going to get there. It doesn't reach the shore since it's going straight that way. On the other hand, the other thing I want to point out, I want to jump back to this observation we made that the tangent of theta was this 0.2582, and the sine of theta was 0.25, that those were really similar numbers. It turns out that for small angles, sine of theta is very similar to tangent of theta, and both are very similar to theta itself if measured in radians. I'm not going to derive the small angle approximation for you. It's a neat thing that it's true. I'm not going to derive it, but it is a handy thing. But if you have a small enough angle, 14 degrees maybe isn't quite small enough. Really, I'd like for this to be 0.1 or less, even smaller, 0.01 really. But for a small enough angle, we can do this small angle approximation. So again, that's theta, what do I want to say? Theta less than or approximately, I don't know, 10 degrees, 5 degrees, 1 degree, whatever. So I want it to be pretty small. I want it to be a pretty small angle. The smaller it gets, the better the approximation is. The small angle approximation tells me that sine of theta, small, is very close to tangent of theta, small, which is very close to theta small itself in radians. That is the small angle approximation. And if that's true, if we're at one of these small angles, and again, 14.5 degrees is borderline. We saw that gave these were about 3% different at 14.5 degrees. If I have a small enough angle then I can take this and say if sine and tangent are about the same, then I can compare those. I can just say that tells me that n lambda over d is sine of theta, theta constructive, which is approximately tangent of theta constructive, which is equal by definition, or by opposite over adjacent, to S over L. And so that tells me that n lambda over d is approximately S over L. And so I could just solve for S right away without any trig functions at all, without ever even checking the angle. I could say that S is approximately n lambda L over d, just solving for S in this equation. And what would that give me? That would give me 1 times 6 meters times 120 meters, these are the numbers from earlier for our problem, divided by 24 meters. And if I work all that out, and make some room to actually write down my answer, if I work all that out, that will give me 6 times 120 over 20, 120 over 24 is 5, 6 times 5 is 30, so this is basically 30 meters. And you can see it's pretty close. 30 meters is my approximation, 31 meters is the correct answer, the more accurate answer using the full equation. So even for 14 degrees or so, this approximation holds pretty well. But to really get it right, I needed to do the full angle version with the inverse sine and finding the angle and then finding the tangent of that. So those are two ways of doing it. If you have a small enough angle, this is a much easier equation to use than all these inverse sines and tangents and things. But in general, you can, if you want to know how many points of constructive interference there are or something, you're going to need to use the full sine of theta, tangent of theta sort of take on this. This is just an example of this two-source interference problem. I hope it gives you a sense of how to solve this kind of problem, how we approach it. And again, this will apply, these same equations will apply for all sorts of cases, whether it's lasers going through a double slit or a pair of loudspeakers or anything like that. This is how you'll solve these problems, and I hope it's useful.